This is 7.6, all about common logarithms. All right, so we want to be able to solve equations using common logarithms and evaluate expressions using the change of base formula. Okay, so you may be wondering, what are logarithms? Why are we using them? Why are they important? And what's nice about logs is that they're one of the few things that we study in here that have many applications in other subjects directly. So if you're in chemistry right now and you've learned anything about the pH scale or acidity of certain compounds, then logs are used there. Okay, so logarithms with base 10. So if we take a log base 10 of something, it's commonly used in other subjects. And this is what the log button on your calculator does. Okay, so if there's no base written, just assume that it's base 10. Okay, they're used so often that we usually don't write the subscript. The log button on a calculator is a base 10 log. So if you have a handheld calculator or a scientific graphing calculator, anything like that, anything in Desmos, anytime you see a log that doesn't have a base, it's assuming a base of 10. All right, so if we're just using a calculator to evaluate these, let's see what we can come up with. Just trying to figure out what is the log of 41,600. We get this decimal, right? So usually we'll want to round to 3 decimal places, 4.619. And then this one, if we do the same thing, we should get negative 0.355. That's it. And notice how if you type just log or if you type log base 10, you're going to get the same thing, okay? So here's where we get a little bit more involved. All right. So in section 7.4, so a couple lessons ago, we looked at examples like this, and I recommended that you take log base 11 or log base 6 of both sides. You guys remember that? So the reason why you might want to do that is because it allows us to reach a point, right, where log base 11 of 11, that would end up canceling out on the left side. We'd end up with 1, so it would kind of ease our problem-solving process a little bit. Okay, but you may be told that your answer needs to include base 10 logarithms. All right, in this case, here's what you should do. You should just take the log base 10. Because it's base 10, I'm going to leave that off of both sides. Okay, so this works every time no matter what. You can also do this with the natural log, which we are going to get to in our next section. Okay, take the log of both sides and then move your exponents out front. Okay, here's the thing though, right? Nothing's going to cancel because we have like a log base 10, log base 10. So our process is going to be just a little bit more involved, all right? So we're going to distribute this log base 10 of 11 to both the x and the negative 3. Okay. And then now we see we have an x here, and then we have an x on the other side. So let's get our x's on one side of the equation. Let's subtract x log 11 from both sides. Okay, this is just another way to solve these kinds of equations. Now we're going to factor out our x again because we're trying to get our variable isolated. So it's the same process that we've done before. It's just a little bit more involved because we can't cancel out any of our logs. And then now we have a number equals x times a number, so we can just divide both sides by this number, negative log 11 minus 4 log 6. Okay, the reason why you might want to do this instead of using the base other than 10 is because now we can just plug this right in using a calculator, okay? Because this is the common log, it's the log base 10, it's the one that our calculator buttons are programmed to accept. That will be our final answer, okay? In exact form. Say we do this again. Pause the video, try this one. Okay, following the same process, you should end up with -9. Excuse me. Let's just work this out. I think that's going to be easier. Okay, take the log of both sides. You get log of 4 to the 5x equals log of 15 to the x minus 9. Okay, you end up with 5x log of 4 equals x minus 9 is going to be multiplied by this log 15, so I'm just going to do that in one step. X times log of 15 minus 9 times log of 15. Okay, get your x's on one side, so we have 5x minus, excuse me, 5x log 4 minus x log 15 equals -9 log of 15. Factor out your x. Okay, and then divide both sides by that number. So you end up with x equals 9 log 15 over 5 log 4 minus log 15. Okay. So that's base 10 log, solving equations with that. I know it's kind of messy, but it's the same process that we did a couple sections ago, all right? So the next part of the section involves the change of base formula. Before calculators got so savvy, so right now, right, we can go to Desmos and we can tell Desmos, hey, we want to plug in log base 4, right? We can put that little subscript of the 4 down there of 5, and Desmos can handle it, all right? Desmos Graphic can. Desmos Scientific, though, remember, it can't handle it. And this is how most calculators have been for a while, up until the last like 5 or 10 years, okay? So log of 10 or log of 25, this calculator can handle that, but it can't handle log base 4 of that. It gives you an error, okay? So in order to avoid that, in order to still be able to evaluate this log, we can use something called the change of base formula, where you take the common log of this number divided by the common log of your base number. Okay, so here's what this would look like. Use the change of base formula to compute this. This is equal to the common log of 1/8 over the common log of 5. You see that, how that b is up here and the a is down here. And then now we can use a calculator for that, right? Log of 1/8, oops, need to be careful by parentheses. Goodness, okay, divided by log of 5. And we end up with -1.292. This one is equal to the common log of 1/6 over the common log of 3. Should equal -0.613. Okay. So let's take a look at some real-world applications of this. Cars purchased for $49,000. Each year it loses 20% of its value. After how many years will the car be worth $16,300 or less? All right, so think about this if we don't know anything about exponential decay, right? A way that you might approach this is by writing out after 1 year, we know that 20% of 49,000 is, see, it's almost 10 grand, not quite. we find out that it's worth 39,200, right? After 1 year. After 2 years, well, we would just kind of do the same thing, right? We'd be worth 31,360, and we could just continue that process, taking 20% of the number that comes next, and then subtracting that from the value, or we could recognize that this is an exponential decay function, right? And so the value is equal to the original number, 49,000, times, since this is decay, we want to know what's 1 minus 0.2. Okay, that's going to be our rate here, because what's left, it's worth 80%. If it loses 20%, it's worth 80%. And we're going to raise that to the power of how many years are happening. To figure out when this is going to be worth 16,300 or less, we want 16,300 to be on this side of the equal sign, okay? The left side. Now we need to solve for t. Since we have the logarithm in our tool belt, we can actually solve this problem, okay? First thing we're going to do, though, is divide both sides by 49,000 because of this multiplication here, okay? So we'll take 16,300 divided by 49,000. And I'm in the habit of just leaving that as a fraction and then evaluating it at the very, very end, okay? And then 1 minus 0.2 is 0.8 raised to the t power. Now let's take the common log of both sides. If you wanted, guys, you could take the log base 0.8. It would actually probably be a quicker way to get your solution. Okay, and then now that t is going to be able to come out front over here. And then we want to divide both sides by that number to get t by itself. Okay, so you're going to end up with log of this whole fraction divided by log of 0.8. That's equal to your t. Okay, so all of that is equal to your t. So plug it into your calculator, right? Log of 16,300 divided by 49,000 divided by log of 0.8. And we get this, 4.93 years. So after equals t, so after 4.93 years, or after like approximately 5 years, that's when the car will be worth that value, okay? Last one is a loan. A loan of 43,000 is made at 4.5% interest compounded annually. After how many years will the amount due reach 57,000 or more? Okay, so if we started out with 43,000 and we know that the loan balance is going to be increasing, we want 1 plus. Okay, 4.5% interest, we want 0.045. Compounded annually means we're dividing by 1. And then compound interest, we have to the raised to the nt power, which is 1 times t up here. Okay, so we want to know when will that be equal to 57,000. I'm actually just going to write that on this side, equals 57,000. And then now we'll just kind of clean up, solve whatever we can. 43,000 times 1.045 raised to the power of t equals 57,000. Divide both sides by 43,000. So I'm not going to divide this because I might get a decimal and I don't want to round my intermediate computations. Okay, and then now we'll take the log of both sides. Okay, your t is going to come out front, and then we're going to end up dividing both sides by log of 1.045. So we're really just going to end up with this right side, right? Divided by log of 1.045. That's our exact answer, which is approximately, if we type it into a calculator, it's approximately 6.4. So what does that mean? It means that after 6.4 years, so about 6 years and 4 or 5 months, so about 6.4, you can write 6.4 years is when that loan balance will be over $57,000. Okay, that's all I got. Check your practice. Let me know what questions you have.